mean to say here, suppose if you consider the scattering phenomenon of the waves, that is for isotropic scattering, if we have the familiar relation like this phi, that is correlation function, so we can express it like right in terms of the total received power of the signal, right, omega p by 2 into j naught of 2 pi fm into delta t. So this is the Bessel function of order 0, j naught of 2 pi fd into delta t, because I'm using notation fd here for Doppler frequency. So this I can now write this fd equal to what? Actually, this fd into delta t is equal to this one. Okay, so this I can write, right, some omega p by 2, right, where omega p is the total received power, omega p by 2 into j naught of 2 pi delta x by lambda, right? So what do you mean by that? The correlation function, the spatial channel correlation function, or the spatial correlation function, if you can write it like this, so this is, right, is a function of delta x, right? So this 2 pi by lambda into delta x, right? From this, what you can see, suppose if you have a delta x, suppose that delta x is equal to something like around 0.38 into lambda. When delta x is 0.38 into lambda, so this basically lambda is what? Basically, it is a spacing between the antennas in MIMO communication. So right, MIMO antennas. So this lambda is the spacing between the antennas. This delta x is equal to 0.38 into lambda. So at this delta x equal to 0.38 into lambda, so your correlation function, that correlation is basically 0. This one. Okay, this tends to 0. It means that we get the uncorrelated signals. So we get the uncorrelated signal. I mean to say that here the message is, so when the two antennas are separated by lambda by 2, right? So it means if the antennas are separated by lambda by 2, the signals received by these these two antennas are uncorrelated, right? So if you bring them more closer and closer, right, then they are correlated with each other, where there is a equal probability of arrival from all the directions. So this is very, very fundamental. So for anyone who is, doing research, right, from the fundamental level. So that is, one should understand what I mean by the spatial channel means, right? And this comes from this one. Okay. So we linked with the user velocity, right? The Doppler shift, and when the user is moving with certain velocity, right? We know these relations, right? We related, and we are calculating the spatial correlation function, which is expressed like this, right? So I said that at a delta x of this much, right? Approximately 0.38 into 0.4 lambda, right? So this we get uncorrelated signals, right? And we should also note here is that, so when you talk about a wireless channels, right, as we mentioned, the angular spread defines the space domain. I mean, it defines the richness or the richness of the scattering and poorness in the scattering, right? So here the rich scattering results in the parameter I am defining, the coherence distance. Right, as I mentioned, when you say the channel variability in time, right, we said the
I request all the participants to be online. Sir will join within 2 to 3 minutes.
Yeah, I'm sorry, there is a sudden interruption.
Okay, sir.
So
okay, sir.
I said, right, the Doppler spread, the delay spread, and in time domain, time variability of the channel, in frequency variability of the channel, we have the the channel parameter delay spread, and here the angular spread I said, right? So we are defining here the coherence distance, right, which is basically the inversely proportional with the angular spread. So here we define in a space domain the coherence distance dc, right? So it means the rich scattering results in the smaller coherence distance, poor scattering results in the larger coherence distance. So it means that this coherence distance, how we define? So it's basically the space in spatial domain, right? So that is basically this is the distance, right? That is the spatial distance. This is the spatial distance. Okay, so spatial distance, so over which the channel does not change appreciably. Okay, so I mean to say that here one needs to understand the angular spread. So suppose you have a base station, we have the mobile, right? So usually in a cellular environment, or if suppose in an environment, wireless cellular environment, so we have the rays, right, with the different delays, right? It comes like this. This is the base station, right? So this is the signals arrived with equal probability from all the directions. Let us suppose here in this environment, right? So we define the angular spread. So it is as the spread of the angle of the arrival. Okay, the spread of the angle of the arrival of multipath component, right? Spread of the angle of arrival of the multipath components, that is AOA, right? Angle of arrival and angle of departure, right? So it means that if this is the transmitter, we say that it is angle of departure here. Suppose this is the transmitter, angle of departure. At the receiver side, it is angle of arrival. Okay, the user equipment is the receiver here. So it means that we usually calculate the RMS delay spread, RMS theta RMS, right? So I mean, in the frequency variability, I said the tau RMS, the delay spread, but here it is the RMS, angular RMS, right? That is the what we call the theta RMS we define from the space domain. Okay, so this theta RMS we usually write it like this for the spatial dimension, right? So like this we write psi of theta d theta, right? So this by over a as we are saying, right? The rays coming from all directions with equal probability of arrival, that is P, the probability density function P of theta. We write it like this 1 by 2 pi, right? It follows uniform distribution, right? That's why it is 1 by 2 pi. So this we write it like this. That is theta RMS. So I mean to say that this theta RMS, this would cause the space selective fading. So like the time selective fading and frequency selective fading, this angle of angular spread, this would cause space selective fading. So then we define the coherence distance. So the coherence distance, as I written here, that the coherence distance DC, it is usually inversely proportional to this theta RMS. Okay, this is very fundamental point, right, in this space domain, right? So the coherence distance is proportional to 1 by theta RMS, right? I mean, if you see, right, suppose if you have the, I mean, you need to know what is the spacing between the antennas, right, in the transmitter side and as well as the receiver side. So I mean, if you see here, suppose if the base station has many antennas, right, the angular spread at this base station is not same as the angular spread here at the mobile, right? So it means that if the base station has have multiple antennas here, base station also uses multiple antennas. Of course, here the user equipment also has multiple antennas. If the base station has multiple antennas, so it is not true that the rays come with equal probability from all the directions, right? That is the angular spread at the UE, angular spread at the user equipment is not same as the spread at the base station. That one must note, right? So it means that we have for the time variability of the channel. So we define the coherence time Tc equal to Tc proportional to the Doppler spread or Doppler frequency, and for frequency variability of the channel, the coherence bandwidth we define, which is 1 by tau RMS, and I mean the coherence bandwidth inversely proportional to the RMS delay spread of the channel, and space domain, the coherence distance, right, inversely proportional to theta RMS, right? So the theta RMS, as we have just defined, right, that is the angular spread. Okay, so that is the more is the distribution of the angular spread, less is the coherence distance. More is the distribution of angular spread, less is the coherence distance, vice versa. Okay, so it means that at the user equipment, so we can place the antennas very close to each other here, right? So because the angular spreads at here at user equipment and the base station they are different, right? But whereas at the base station, right, we need to place the two antennas far apart to get the uncorrelated signals, right? Or to get the uncorrelated signals, we need to place the antennas, two antennas far apart, right? So because it depends on the channel fluctuations, right? That is what distance the signals are uncorrelated, one needs to know. We have to know. So it means, right, if the two antennas are rubbed like this, two antennas, right? So this delta x or x, right? This separation is very important. Okay, so in time domain and frequency domain, right? That is for time and frequency variability of the channel, right? We have the larger chorus bandwidths and the chorus times also, right? But usually when the demerit is if the signal is in that state, means where we have the larger chorus bandwidths and larger chorus times, right? The signal usually it would not come out of that state. But whereas in the space domain, so it is not a function of the time and space. This in the space domain. So this is separation. It is not a function of the time and space, but it is a function of the space. It is a function of the space. So if this is the small, we can place the antennas closer, right? So I mean, just to give you like a real example, right? If you take the mobile, if you take your mobile, right, of 5.5 inches, right? 5.5 inches wide. So you can easily place the two antennas on your mobile phone, right? At a certain frequency, like suppose 2.4 gigahertz. Whereas at the base station, so we need to place them far apart, right? But the distance would be manageable. Okay. And we also said that we also keep in mind that this correlation function, right, which is a function of this delta x, right? Delta x we have written already, right? This is omega p by 2 into the j. So this is j naught of 2 pi delta x by lambda, right? So the smaller the values of lambda, right? So this would affect the coherence distance, right? That is coherence distance is short compared to larger values of lambda, right? So the coherence distance at base station is roughly usually the 5 lambdas, whereas this is at the base station at BS. But whereas at the UE, whereas at the user equipment, it is 0.5 lambda, right? See, it is lesser, right? I mean, the spacing is lesser at the user equipment, and at the base station, it is usually more, 5 times of lambda, right? It depends, right? I mean, if you take the 2D isotropic scattering at lambda by 2 spacing, right? So it is uncorrelated at 25% only, right? So uncorrelated at uncorrelated at a point to 25%, and the correlation becomes 70%. And we should also note that in order to be uncorrelated and uncorrelated signals here, we need to have the spacing lambda by 2 at the user equipment, right? And more important in the spatial channel modeling, in this MIMO spatial channel characteristics, right? So one needs to understand in terms of both the time domain, frequency domain, and the space domain, right? So that is in terms of the time domain T, F, and the space domain. So in the space here we define the for the channel models. So we define usually, I mean, most of you people might be knowing this. That is wide sense stationarity, wide sense stationarity, right? Uncorrelated scattering, wide WSS uncorrelated scattering, right? So in this, I mean, wide sense stationarity uncorrelated scattering channel model. So here, what is the message here is that in this, the channels at two different Doppler frequencies are uncorrelated, right? It means that depends only on the time lag between the two channel coefficients. Okay, that is what we mean by the uncorrelated WSS scattering means. It means, right? So it depends on the time lag. That is at the signals at two frequencies, F1 and F2. If you take at F1 and F2, they are uncorrelated, right? That is a correlation function is dependent only on the time lag, right? Our channel at two Doppler frequencies are uncorrelated. That is called WSS means. Okay, I'm not going to write any mathematics here. I'm just giving the message, right? So channel at two different Doppler frequencies are uncorrelated. That is called the WSS means. Okay, wide sense stationarity and uncorrelated scattering means. And the one more is that is WSS uncorrelated scattering. It means that the signals at two delays, right? Because as I said, the signals arrive with different delays, right? At a different delays, right? Maybe poor or risk scattering, right? So when you launch an impulse here at the base station, right? So the in a space domain, right, the delays correspond delays. The signals with the different delays, right, are uncorrelated. The signals at different two different delays, like for example, tau1 and tau2, they're uncorrelated, right? The channel coefficients at the channel coefficients are only at two delays are uncorrelated, right? Or you can say the channels at two different frequencies are uncorrelated, right? When you separate them in frequencies, right? That is called the uncorrelated scattering. And homogeneous, there is in a space domain, right? In the space domain, signals at two different points in space are uncorrelated. The signals at two different points in space are uncorrelated, right? They are actually the function of coherent distance, right? So they are as a function of coherent distance. I repeat, the signals at two different points in space are uncorrelated. So that is called the homogeneous, HO, we say it, right? So I told here WSS, right? That is on the white sense stationarity, right? That in the delta T, right? In so where in the signals in two different frequencies are uncorrelated, and uncorrelated scattering, it means that, right? It is delta F, right? With two delays. At two delays, they are uncorrelated. Depends only on the time lag. In it is this here frequency lag, and this one is homogeneous scattering. Means homogeneous channels means the signals at two different points in space are uncorrelated, right? It is a function of the coherent distance, right? Here you can say theta1 comma theta2. So this is the delta D distance. This is frequency separation, space domain separation, time domain separation, time separation. Okay, so one must know the difference, these fundamentals. Okay, so this is called the spatial channel characteristics. Okay, your entire MIMO communication analysis depends on this. Okay, so the analysis, mathematical analysis, or say MIMO signal processing. Okay, and you know the expression for the we have usually different modes in communication. You people know, right? So when you talk about the MIMO communication, we say it is a single input, single output, single input, multi output, and multiple input, single output, right? And multiple input, multiple output. So this we know, right? We have the at the transmitter side, or if you take an example like mobile communication. So at the base station, we have one antenna. At the UE, we have one antenna, right? And at this CMO, right? Single input, multiple output, right? So we have at the base station, we have one transmit antenna, right? So it is like this. So this is connected to the transmitter, and we have the antennas like this at the receiver, right? So they're all connected to the receiver like this, right? So this here I launch a signal symbol with S of T. It is like this, right? So we have different links here, right? So what do you mean by this? Different copies of the same signal is achieved here, right? Different copies of the same signal. My signal is S of T, different copies of the same signal. So that's why we say here receive diversity. We say this is a receive diversity system. This is called a receive diversity system. The receive diversity, that is SIMO brings receive diversity, right? So one is to understand how the channel would be. How would the channel would be, right? So here you can say this is user equipment and this is the base station, right? Means that we are describing the system here, the uplink, right? From the UUT, the user equipment to the base station is, right? So your user is your mobile phone is the transmitter and the base station is the receiver, right? So your channel has coefficients like, right, H1 of some delay tau comma T, next channel coefficient tau comma T, H2 of tau, or likewise we have some MR number of antennas, receive antenna HMR of tau comma T, like this. Okay, so it means that your channel has a delay, right? Tau comma T, right? So we have we have different channel coefficients here, right? So it means that this is basically what is H of tau comma T. It is an impulse response of the channel. This is the impulse response of the channel. Of course, we can write here HI because we have, so it is going up to MR. So it means that for the ith branch, so it means the transmitter antenna one, I mean the TX, but the ith receiving antenna. So where I is taking values from 1 to MR up to going up to MR. So that's why we have written the channel matrix like this, right? Like H2 of tau comma right? T. And so let us suppose we assume a delay of tau here, right? For the scatterers. Okay, so it is like this. So it's basically a column matrix. So it is a column matrix. If you can write it like this, basically it's a column vector, right? We have H1, H2, H3 like that, H1, H2, H3, and so on up to HM, HMR. Okay, so like this. I mean, this is basically I'm writing an expression for the SIMO channel, single input multiple output channel, right? So here we can write like we have the outputs yi of t because we have the different branches, MR branches here at the receiver side because it's a receiver diversity system. And assume that you may think of right what kind of a fading you are experiencing here. Remember that it is usually we assume that flat fading, slow and flat fadings, right? Because I am assuming that taus are same here. This tau here same. Delays are same, right? Only tau, right? Delays are same here. So I can write H. It is like this column vector. So then yi of t. So it is like this hi of t convolution with s of t. This s of t means this is what I'm launching a signal, right? I'm sending s of t signal. So it basically does the first linear convolution, then circular convolution for right, usually, right? So this convolves with the channel hi of t with the s of t, we will get yi of t. So I mean to say that the different copies of the same signal you can appear here. So this same signal, but different copies you can see at the receiver. Each of this link would have the, of course, noise associated with this. This is one link, this is another link, another link. Each of the link would have noise associated with this link. This is called the SIMO. This is called the received diversity system, right? And the transmit diversity system, right? The transmit diversity is the MISO, multiple input, single output, where you can have your transmitter. It is you have many antennas like this, right? Many antennas which are separated by a distance delta x, as we discussed already, and this is your transmitter. So but we have here different copies of the different symbols, or you can say different signals you transmit up to SMT of T. Okay, MT means number of transmit antennas. We have the we send here different signals, right? But at the receiver side, we have only one receiving antenna here. Okay, so like this. So note down this. This is a diversity is achieved at the transmitter side here, right? Diversity is achieved at the transmitter side. So this is basically a row vector now, right? Because it's a multiple input, single output. So this would become the row vector here. Okay, your h of tau comma t. This is a row vector, but here it is a column vector in the SIMO system. But in MISO it is a row vector, right? So I mean it is like this. You can write different. This is h1. Next one is h2, and so on up to it will go up to hmt, right? Which is a function of time, right? h1 of t, h2 of t, and so on up to hm of t. So this will become a row vector h1 of t, right? This is h2 of t, right? This will go up to hmt of t. Okay, so this is a row vector. Okay, so now here also it does a convolution with the transmitted signal. So it is basically you can write hj of some tau comma t convolution with sj of t, because here we are launching different, right? This copy through different antennas sj of t, where j is taking values from, right? Like for example, some m equal 1 equal to m 1 j equal to 1 to mt, right? The empty number of transmit antennas, right? So this is a convolution, right? This you will see, plus anyway the noise would be there. Noise would be there. This is equal to your y of t. This is equal to your y of t. This is your received signal. Y of t is your received signal, right? This we have only one y here, but whereas in the SIMO system, in the previous system, we have many y's, right? So because that is the receive diversity, we have many y's, but in transmit diversity, we have only one y of t, right? So this we have this is the single, right? This is single vector, right? This is a single, sorry, this is single scalar, right? We have only one y, and this is a row vector and column vector. So this is the column vector, and this is the row vector. Your channel matrix is the row vector. Okay, so this S of t is actually you can write like S1, S2, and so on, Sm of t transpose. You can write that way because it is a S is actually here. It is a column vector, right? You can write that. So now just quickly going into the MIMO now. So in MIMO, what we'll do, we have the combination of this CMO plus combination of CMO plus MISO. So this is MIMO. Okay. So in this MIMO, so in MIMO we have, we have MR transmit antennas, MT transmit antennas. As I mentioned here, right? Here, right? We have MT here and we have MR there in the CMO, and in MISO we have MT, right? If you club both, then it becomes MIMO. If you club those, right? So it becomes a MIMO system. So combination of the previous two cases, right? So remember, it's like, I mean, your channel matrix is like this. We have H11, right? H12, and so on up to, right? Like H1, comma MT of T, and this one is H21 of T. Anyway, this is a function of time, right? So remember, these are all channel matrices, right? So I mean to say that just to tell you, right, this is your transmitter and this side is a receiver, right? So we have the links, right? Like this, we have the different antennas here. We have many antennas which are connected to the transmitter. This is a transmitter. And likewise, we have many receiving antennas. We have many receiver antennas which are connected to the receiver, right? So you can form the links like this, right? So it's basically, I mean, this matrix is basically the MIMO channel matrix. H11, H12, and so on up to H1MT, H21, H22 of T. Likewise, we have HMR of T, right? HMR1 of T, and so on. This is HMR, MT of T. So this is your channel matrix of a MIMO system. So you can assume on each component, right? On each channel coefficient we have, right? It is basically a flat fading. It experiences flat fading, right? So, and I mean, maybe, how you read this H11, H12 means, right? So this H12, it means that, right? So this is the received in antenna 1 and transmitted from antenna 2. So this is transmitted from antenna 2, received in antenna 1. That is the meaning, right? So this H1 means received in antenna 1 and transmitted from antenna 1. Okay, so that is the way you have to, read, right? So that is the nomenclature basically. Okay, so the difference is actually here. You can write the y of t, right? So both transmit diversity and receive diversity is achieved here. So this also a convolution between the impulse response of the channel with the transmitted signal. So, but whereas this one here, it is taking both I and j. So where this j is taking values up to MT and I is taking values up to MR, right? So this yi of t is equal to the convolution between the impulse response of the channel and the transmitted signal, where, right, Sj of t, where j is taking values from 1 to MT, right? As I mentioned, 1, 2, and so on up to MT. Okay. So finally, we write a matrix yi of t, right? This is a vector. Yi of t is equal to h of t with s of t, right? So note down, this is a matrix, h of t, this is a matrix, right? And s of t is a vector and y of t is a vector, right? And anyway, noise, obviously, it would be there associated, right? So we have, right, the y of t here, right? This is in y of t, right? So the size is anyway mr cross 1, right? And this is mr cross mt, and that is this channel matrix mr cross mt. And this is mt cross 1, and the noise is mr cross 1, because noise means, I mean, here the received diversity at the receiver side, right? Noise, we usually see that at the receiver side. So this is about the MIMO simple channel expressions, right? So it is simple. So if your MT number of antennas are same, single, MT equal to 1, MR equal to 1, then we see it is CISO system. If it is MT equal to 1, MR equal to MR, then it is CMO. If it is MT equal to MT and MR equal to 1, then it is MISO. If MT and MR, if you consider, that is MIMO, right? So the study of this MIMO communication is based on this model. That's what the message. The study of the MIMO communication, right, is based on this model. Right now, just to quickly tell you, I mean, usually when you, I mean, research on this MIMO channel modeling, MIMO channel models. So one should also know about what do you mean by the classical IID channel, right? The classical IID channel. So the classical IID channel means usually what do you mean by the classical IID channel here is that, so the channel matrix, this H, right? So this usually we model as the zero mean complex Gaussian circular symmetric ZMCGCS, or you can also say that zero mean complex circular symmetric complex Gaussian with unit variance, right? So it means that, so this H matrix, it has right, this H matrix has H11, H12, and so on, right? These are all basically the channel coefficients, which are basically random variables, right? So these we can model it as a circular symmetric complex Gaussian random variables. So complex Gaussian means what? Z, suppose Z equal to, if you write, right, the Z equal to X plus IY, right? So this is, if you take the expectation of this mean, I mean, the expectation of Z means mean, right? So this is equal to 0, right? So this e power, this expectation of this Z, it is 0. That is called zero mean, right? So it means that they are the complex Gaussian, they are the complex random variables. They have the zero mean and the same variance. That is called the circular symmetric means. So this is called circular symmetric random variables means. So they have the zero mean and same variance, right? And they are independent of each other, right? This X and Y. X and Y are independent of each other, right? So that is called the zero mean circular symmetric complex Gaussian random variables means, right? So if you see the correlation function also, so the correlation function, if you can write the correlation function for this both, I mean, for in-phase and quadrature, that is X and Y, for X and Y Gaussian random variables, right? So here, this is 0. So it means they are zero mean and uncorrelated, right? They are zero mean and uncorrelated. Okay, so they are Gaussian random variables. They are zero mean and uncorrelated random variables, right? And it means that they are independent. Okay, so this is for, I'm talking about for the classical IID MIMO channel means classical IID channel, right? Means it should satisfy this property, right? So and for this matrix H, these H components means this the spatial matrix. This usually called as this as a spatial matrix. These components are made up of this X and Y. Okay, so these are all made up of this X and Y, right? They are independent zero mean and they are having the same variance, because we are saying that this is zero mean complex Gaussian circular symmetric random variables. So this also should satisfy the property of this H W. This is 0. I mean to say that W means white, right? So white channel. This is a spatially white channel, right? So E the expectation of H of W, this is equal to 0, means elements of this elements H W means all these elements of this H matrix. If you take the mean of these, this is 0, right? So for a spatially white channel, the mean is 0, right? And the power, if you calculate the power, that is the E of H W of I comma J, right? This square. So this is equal to unity usually, right? And if you also calculate the uncorrelatedness of it, if you see the uncorrelatedness, right? So then we can write the H E of H W of Ij and H W of M, right? Conjugate. This is equal to 0. It means, and this is if I not equal to M and J not equal to M, right? This way you should see. I mean, they are uncorrelated, right, with each other. They are uncorrelated with each other, right, and they are Gaussian. So that is this channel. These are all uncorrelated with each other, and they are Gaussian. Okay. So these, if any channel, MIMO channel satisfies these properties, right, we say that that is a classical MIMO IID channel, right, independent and identical distributed channel. So that is the spatial channel. Okay. So this is one more important point. Now coming to the spatial diversity, right? So because the spatial diversity is very important, usually when you consider the MIMO system. So I'll take 5 to 10 minutes more, then I'll close my session because it's already 12. So if I'm allowed to take 5 to 10 minutes more, then I'll continue. Otherwise, I'll stop.
Okay, sir, no problem, sir. You can continue.
Yeah, I'll continue for 5 to 10 minutes more.
Okay,
Madam.
okay.
So
Sure.
I just highlight the what do you mean by the spatial diversity and the importance of the diversity, right? I mean, two primary things one should understand when you study the MIMO systems, right? So we say that when you say the MIMO systems, so we have to know about the spatial diversity. Spatial diversity and the spatial multiplexing. Spatial multiplexing. Okay, so it means that as I mentioned just now, we have the 4 modes, right, of the communication. So single input, single input, multiple output, right? Multiple input, single output, multiple input, multiple output system, right? So it means right when you look at the diversity, right? So we have here at the input side, that is we have at the input side, right? That is the transmitter side, and at the receiver side, right? So here, of course, we have multiple antennas, and here also we have the multiple antennas. Right? So our aim is to get the diversity gain out of these 4, right? What is the advantage of this having these antennas spatially separated, right? So we get the we get the diversity at the receiver side. Sometimes that is we say that is CMOS system. We get the obtain diversity at the transmitter side. That is a MISO system. And if you get obtain the diversity at both the transmitter and receiver side, that is MIMO system, right? Multiple input, multiple output system. So it means that to obtain the diversity at the transmitter side, one needs to note that. So we need, we need a feedback of the channel information, that is H, right? The channel information is one channel information that has to be fed back. Okay, we may need a feedback of the channel information, right, which is to be fed back to the system, right, to obtain the diversity at the transmitter side, right? And we may not need feedback also. It means we keep on transmitting the signal without waiting to get the channel information at the transmitter side. That is also one kind of analysis in the MISO. I mean, so the when you obtain the diversity at the transmitter side. Okay, so note that here our aim is to get the diversity out of these 4 systems, right? So, and once again, in the diversity, you beam that when you send a signal onto the air, right? We would like to receive multiple copies at the receiver. That is what, in simple way, right? So it means the diversity usually it can be obtained in time domain. As I said, in a wireless channel, we can obtain in time domain. You can obtain the diversity in frequency domain, right? And the space domain, right? So we are most interested, I mean, here, right? So this because in space domain, right? So what you said is the rich scattering, poor scattering, and the coherence distance, the angular spread we are defined, right? Anyway, so it means that the diversity can be obtained in time, frequency, and space domain. Diversity means when you send a signal onto the air. So basically, I would like to have, or I would like to receive multiple copies at the receiver, right? So we could receive the copies in time domain, frequency domain, or in space domain. Okay. So in time domain, when you send a signal, for example, some x of t, right? So you can receive a copy like with a different at a delay, right? Suppose I receive a copy, one copy x of x tau of t, and another one with some delay tau, with a delay tau, right? Like this. So I can. It means that we receive the x at a delay, some delay at some tau naught, right? Maybe a tau 1 and so on up to some tau n, right? So if I mean, that is if x is received at a tau naught, tau 1 and tau n, they are uncorrelated, right? They're uncorrelated. Then we get some, what we'll do, I mean, we'll basically get some benefit out of it. Okay, so in frequency domain, so we can write like, suppose I send a signal with the x of f, right? And I receive with similarly for x plus delta f, right? It means the receiving signal at 2 different frequencies, f and delta f, they're uncorrelated. Here in time domain, they are uncorrelated. Here in frequency domain, they are uncorrelated, right? Means if I send the same signal at 2 different frequencies, right? I send the same signal at 2 different frequencies, that is x of f1, x of f2. But here it is in time domain, right? So so we in wireless communication especially, right? So we know that the right usually these are all costly. The time and frequency, they are costly, and we have different ways of achieving the diversity gain. So that's why people go in analyzing in the space domain. Right, in the space domain means we have different ways of achieving the diversity gain, right? So in spatial dimension, how it would be usually. So in spatial dimension, so you can look at the problem like this. So let us suppose we have the flat and slow fading channels, right? So if you see the signal, how it varies, suppose this is so this my signal is varying, right? So where my received signal y of t, if you take the mod square, right? So this usually follows the other distribution like exponential distribution. This is basically envelope squared, right? So we analyze it like this, right? So we usually define the level crossing rates. So in a communication system, wireless communication systems, right? So I mean, I'm analyzing my system, right? At the transmitter and receiver side, right? In terms of the diversity, right? So this y-axis, note down this y-axis is the time, right? So my received signal, right? It's varying like this with respect to time, right? So I'm saying this is the envelope squared follows the exponential distribution, right? So I mean, if sometimes it is going, this is what the level crossing rate, and there is another parameter to define is the average fade duration, right? Our average duration of fade and level crossing rate. These are the parameters to define when the signal goes right above the threshold, below the threshold, right? So if it goes below the threshold, then we say that it is an outage below the threshold. Here it is an outage. Here it is an outage, right? So when we usually define, right, what we usually define is that the received signal strength, or in terms of SNR, received SNR as a function of time, right? I can write usually when you define the outage probability of my gamma, right, which is a function of time, it must be less than some threshold, gamma threshold. This is usually the probability. This is the probability. Okay, so it means that we would like to have this probability as low as possible. I mean, this is actually designed, right? So to want this probability low, right, what we do is that so we increase the level of the transmitter. When I increase the level of the transmitter, what it will do? It would be like this. This will go like this, something like this, channel variation, right? So we increase the level of the transmitter so that my received signal strength is increased. So there is hardly any probability, right, that the signal goes below the threshold, right? For the first one, it is going below threshold where your outage is worst, right? Your outage is more. So it means that so we are increasing the transmit power. There is basically a margin, right? So this signal has increased now, right? It has gone up, right? So, but whereas another situation is if you increase, I told this for a single transmit, single antenna system. Single antenna means single transmit, single receive. But in spatial domain, the scenario is different. So we have the in space domain, right? The antennas are separated. Their antennas are separated like this, right? So the separation between this is delta x, right? So like this. So we have the receiver side like this, and we have the transmitter side like this, right? So I transmit a signal x of t, right? So it means we receive another copy of the signal at the antenna 2, right? Another copy of signal at another antenna, right? And here the distance of separation is very important here, note down. And if this distance of separation delta x, if it is less than the coherence distance, right? So the signal received at two antennas are correlated, right? So whereas if delta x greater than the coherence distance, right, they are uncorrelated. Okay. So if delta x greater than this d suffix c greater than, then we say that they are uncorrelated, right? So it means when the signals arrived at the antennas with equal probabilities, that is where you can write the p of theta is 1/2 pi follows uniform distribution, right? So then we calculate the correlation function, right? So then the signal received at antenna 1 and antenna 2 are uncorrelated. It means that my correlation function is going to be 0. Okay. So then if you take both signals simultaneously, if you take both signals, suppose you are receiving one copy at antenna 1 like this, something like this, and another antenna 2, some like this, right? Now, if you take these both signals, this is for antenna, let's suppose antenna 1, and this is for antenna 2, right? So if you take the both signals simultaneously, so then what we'll do in the spatial diversity, we devise a method by which we select the best out of 2. So some means it we take sometimes we select this one, we select this one, we select this one, right? So basically, which is the best, right? Whichever is the higher, we select that. Whichever is the higher, we select that. Here we select this one, we select. Here we select this one, right? So it means we devise a method which select the best of 2. So we have not used the extra power here, right? I said here we have used when you use the extra power, right? So this is going up, right? I'm wasting the power basically. So instead of that, if you keep the many antennas at the receiver side, so I mean within the several tens of coherence distance within a certain region, right? So here we have not used the entire power, right? I mean extra power. We have kept the same average power within several tens of coherence distance, right? Even though your individual links, even though your individual links go below the threshold, right? So even though your individual links going below threshold, your resultant signal, right? Which is the best of these two, it is always above the threshold. Okay, so it is hardly going below the threshold, right? It means that by virtue of getting independent signals, right, in these two branches, these two branches are you can say many branches, of course, here there are many receiving antennas, right? So by virtue of getting independent signal in the many branches, right? So there is a possibility that the probability of the received signal strength goes below the threshold becomes very low. So this is the advantage due to diversity. This is called the advantage due to diversity, right? So we are not using extra power here. That is not increase the power. We are not using any time in terms of time T1, T2, or in terms of frequency also, right? So each receiver branch has their own receiver circuitry, right? So only thing is you may worry about here is that the receiver cost would go up, the receiver power consumption would go up, right? So because we have to process many signals here, right? Of course, this is two branches. In case if you have multiple branches, there should be multiple, right? There are so many like this, so many branches for different antennas, right? So because we have to process many branch signals, right? As we have to, because we have many MR number of antennas, right? So signal processing complexity would go up in the RF side, RF section side, signal processing complexity would go up, right? So by this, right, we get the signal out of the D-fade duration because we are selecting the best out of many. So we get the signal out of the D-fade conditions, right? When compared to the single antenna. So this is the motivation to go for diversity. This is a motivation to go for the diversity. Okay. So I would like to stop the session here. If there are any questions from anyone. So I took this at more fundamental level. So if anybody wants to have any questions, I'm ready to answer. That's all from my side.
Okay, sir. Thank you, sir. I request the participants to ask for any queries if you have.
Sir, good afternoon. This is Dr. Manish here.
Yeah, good afternoon.
Yeah, sir, I have one query. You were talking about the communication channel and you talked in depth related to the diversity, right? So,
Yeah.
Actually, I'm working at the component level, designing MIMO antenna. So,
okay.
There also we take the parameter called the diversity gain. So
Okay.
how this is correlated? That diversity gain related to the component is correlated with the theory which you explained over here.
Yeah, actually, you are designing an antenna. There, you have to calculate for each antenna spacing. You have to consider these parameters, and you have to calculate the diversity gain. Actually, more mathematically, go diversity gain, because once you have to calculate diversity gain, and if you see in the spatial diversity gain, it sometimes when you place more antennas, the diversity gain also it goes down. It will decrease also. Okay, that's why there is a limit to the number of antennas. So your query is, I mean, how that at a component level, how this is related to the diversity gain. Correct?
Yeah, and actually, and moreover, sir, the maximum value of the diversity gain we expect up to 10 dB, right, sir?
Okay, yeah, these are the numbers. Yeah. That is up to, but considering how many antennas and for what antennas and what frequency, and you have to write the spacing. They are all matters.
Okay, sir. Thank you so much, sir.
Thank you very much. Any questions,
I
please?
request any queries, please, from the participants? Otherwise, I request all the participants. Okay, sir, please continue. I request all the participants to turn on your video once to take a pic of today's workshop.
Share another video.
Dr. Subbarao sir, kindly stop sharing your screen.
Oh, okay. Yeah. You have done it.
I request all the participants to please turn on your video once to take a snap of today's workshop. Again, I'm requesting all the participants to please turn on your video once. Okay, you can turn off your videos. So, Dr. Subbarao sir, on behalf of our department as well as our institution, we all thank you for accepting the invitation and given such a nice presentation, which has enlightened all our participants. And you have given a nice presentation on 5G physical layer structure, that as well as
presentation.
Ma'am, your voice is not audible, ma'am. You have muted yourself.
yes. Sorry, sir. Okay, sir. Dr. Subbarao sir, thank you for accepting our invitation. And on behalf of our institution as well as our college, we are very much thankful for you for giving such a wonderful and enlightened presentation on various technologies that range from 2G to 6G. And you have also extended the same towards the orthogonal time frequency technology. And you have described the various applications of 5G communications and MIMO wireless spacious channels, as well as scattering channels and the concept of diversity. And this will be very much useful for all the young budding researchers in the area of antenna towards 5G communication. Thank you, sir. Thank you for once again for accepting our invitation.
Thank you. So I thank the authorities for giving me this opportunity. Thank you very much. So can I leave the meeting now? Shall I leave it?
Yes, sir.
Sir, can I ask you one doubt, sir?
Sir, some queries from the participants.
Yes. Yes,
sir, may the new technologies for OFDM, like multiple access techniques.
Could you please speak louder? Actually, I'm not getting your voice.
Sir, can you suggest a book related to this theory which you explained, sir?
On which, and for MIMO channel model, spatial channel models?
Yeah, exactly, sir. Yes.
I suggest Professor, the book Spatial Channel Models by Arogya Swami Paul Raj, because he is actually father of MIMO communication. So
Okay,
you
sir.
please refer to that. So that
Sure,
is a very
sir.
standard book.
Sir, are
Thank you so much, sir.
Thank
there
you.
any new OFDM techniques, sir?
New OFDM techniques. So
Yes,
it's
sir.
not new OFDM techniques. Actually, OFDM has been used in 4G and as well as in 5G also. But for 6G, it is different waveform. So you mean to say a specific OFDM technology? Could you bit elaborate? I mean, I didn't get your question. New OFDM technique in the sense?
So of multiple access techniques, sir, to do research.
Yeah. So this space division multiple access, right? If you want to work on this MIMO communication, you have to understand this the space division multiple access technique. On space domain, how it is multiplexed.
Okay, sir.
So, I mean, I would suggest you, I mean, if you are researching on this, I would suggest you to know on multiple access carrier interference, I mean, the successive interference cancellation techniques.
Okay.
At the receiver side, we do the, if you do that receiver side processing, multiple access, successive interference cancellation, OFDM and OTFS. If you understand this, you can do very good research. OTFS and OFDM, because most of the people are working on OFDM and OTFS both.
Okay.
There is a OTFS, which is going to be a promising technology for the beyond 5G and beyond, that is 6G, which is expected to be, which is based on a very attractive waveform, orthogonal time frequency space. So if you know, I mean, thoroughly about that, people will definitely appreciate and you will get very good transaction papers.
Okay, sir. Thank you.
Any
Any other
queries
questions?
from the participant side?
Any
Sir,
questions? Yeah.
may I have your contact
Yes,
details?
please.
Will you please share?
Sorry, I mean, I didn't get your question.
Contact details, sir.
My contact details. So my contact details, you can contact me on bsrao26@gmail.com. I'm giving my email ID, bsrao26@gmail.com.
Okay, sir. Thank you.
So, and just to have a note, actually, I forgot to mention. So we are researching on this 5G testbed development here. We need the people. If anybody would like to do PhD, you are welcome. On MIMO spatial channel models and the OFDM, OTFS, right? And 5 and MAC layer technologies of 5G and 6G OFDM waveforms, 6G waveforms. So you are welcome. So you can mail me directly. You can write to me, and please send
Yes,
your
sir.
CV also if you want to work with me.
Yes, sir. Sure, sir.
bsrao26@gmail. bsrao26@gmail.com. Any queries?
Any queries from the participant side? Otherwise, we can wind up the session. Okay, sir. Thank you, sir, Dr. Subbarao.
Okay. Thank you, madam. Thank you. Thanks for giving me this opportunity and interact with the people, I mean, the participants. Thank you very much. Okay, I'm leaving.
Now I request all the participants to be back by tomorrow morning, 10 o'clock for the next session. You can leave the session.